how trivial bundles.
Thank you. Thank you. So let me begin by thanking the organizers for the invitation to give the talk, and best wishes to Oscar on his birthday. Okay, so M is a compact, complex manifold. E over M, a holomorphic vector bundle. We call that a holomorphic connection. Connection on E is a first order differential operator. Holomorphic differential operator satisfying the Leibniz identity, which says that for locally defined sections and locally defined functions, locally defined holomorphic sections and locally defined holomorphic functions. So the curvature is this way. D is called integrable or flat. This square is equal to 0. Now, when you have a flat connection or integrable connection, you have the monodromy. Using parallel transport, you can have the monodromy map homomorphism. Let's give a notation. Monodromy of B. Pi on of you have the monodromy when D is flat. Integrable. Using parallel translation. E is called étale trivial. If there exists finite étale cover connected, let me put M tilde to M such that pi up star of E is holomorphically trivial. Trivializable. Okay. Let us make a small, fairly straightforward lemma. E is étale trivial. If and only if E admits and integrable holomorphic connection with finite monodromy, whose image with monodromy has finite image. Monodromy homomorphism has finite image. So proof. If D is such a connection, take the kernel of the monodromy. Kernel of monodromy. Consider the covering corresponding to this finite index subgroup, and then connection becomes monodromy becomes trivial. So by parallel translation, I can trivialize the bundle. Conversely, here holomorphicity is needed. So suppose it is ethyl trivial, so I can take pi to be Galois by taking further covering without loss of generated pi Galois, such that pi upper star of E is trivializable. Then you have the trivial bundle pi from M tilde to M. So you have the trivial bundle M tilde cross H naught of pi upper star of E. We have the evaluation map. Since it is trivializable, this is an isomorphism. The action of the since E is pulled back from below, the group Galois group acts on this. So Galois group on H acts on these global sections. So this map is equivariant. So these are the Galois group action, and this is equivariant. And it has a trivial connection because it's a trivial bundle, and that trivial connection is preserved by the Galois action. So it descends to a connection here. Right. So the trivial connection on M tilde cross H naught descends to a connection on pi upper star B, which is clearly flat with finite monodromy. Now, so this also shows that any ethyl trivial bundle, this doesn't depend. Finally the connection you obtained on E doesn't depend upon the choice of the covering. So that is easy to check. I'll make the comment because you need it at some point. Ethyl trivial bundle. Has a tautological integrable holomorphic connections with finite monodromy. I started at what time? Now I'll define something finite. Take a polynomial P. AI t to the power I from 1 to n, I from 0 to n. Take a polynomial such that All the coefficients are non-negative. So given a holomorphic bundle, I can plug into this polynomial. So P of E for a holomorphic is defined to be direct sum E tensor to the power I. This is tensor and this is direct sum. Yeah. If it is 0 means trivial bundle, trivial line bundle. And this is 0 means this is 0 bundle. So I can define, evaluate polynomial on vector bundles, holomorphic bundles. E is called finite. If there exist two such polynomials P such that P of E is isomorphic to Q of E, holomorphically isomorphic to Q of E, so finite. So now I take a theorem. E is finite if and only if E is ethyl trivial. So this is for compact complex manifold. Nori proved it for complex projective, smooth projective. Using algebraic geometry. His idea is to using hyperplanes, cutting down, reducing to the case of curves, and curves then we form a Tanaka category for the curve, from this condition, it showed that the monodromy is still finite. The reduction is taken. Anyway, but it holds for compact complex manifold. That's next another criteria. Theorem. This is Dumitrescu, Sorin Dumitrescu. Is ethyl trivial if there exists a surjective surjective holomorphic map phi from f from x to m, where m is compact, x is compact, such that f upper star of E is holomorphic actually.
So this condition on M, it's a complex manifold.
And it's a surjective map.
It's
Compact.
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 X also compact.
M is a sorry, yeah. X is compact, yeah. M is compact, X all are both are compact. I started with compact, so X is compact. Surjective is the key. Okay, now one way of course obvious because as you saw with this, there's some metal cover, it becomes trivial, but okay. So now let us take the category. Most of what I'm saying is joint work with Dumitrescu, Sorin Dumitrescu, João Pedro dos Santos, Lynn Heller, and Sebastian Heller.
This builder, do you have any property of the back? Can you make it flat?
No, I mean, one way is if that will be restrictive. My point is that if there is a subjective map, then it is holomorphically trivial. You don't need any condition. If you put some condition, then it will become restrictive. Yeah? Okay. Okay. Now I will consider pairs E comma blah. E is a trivial. And nabla holomorphic connection only. Note that consider all category of all pairs. So this is closed under direct sum, tensor product, and taking dual. Taking dual. Before when I defined holomorphic connection, I should have said a comment, made a comment which I forgot to. If a coherent analytic sheaf admits a holomorphic connection, then the sheaf is locally free. So that's a very useful thing that comes up again and again. Any coherent analytic sheaf with a holomorphic connection has to be locally free. Okay. So now, what is this? If you have a homomorphism, then suppose any map, then kernel of H, co-kernel of by homomorphism means a map of coherent sheaves such that it takes intertwines nabla and nabla prime. So standard definition. I mean, homomorphic sheaves such that takes one connection, intertwines the two connections. So kernel and co-kernel lie in this category. It has a faithful fiber functor that sends any E similar to faithful. You're welcome, sir. So this category forms a neutral Tanaka category. That is called. I'll use the notation. Well, notation is certainly bad notation. E for ethyl trivial. So that's a. So this one, pro algebraic. Affine group scheme. What's this? So this Tanaka category defense. Okay, now recall that any ethyl trivial bundle has a tautological.
The dual group, the dual Tanaka group.
Yeah, Tanaka category. Yeah. So it's representations of the. No, I didn't put the flat condition. Soon it will be. Soon I'll talk about Riemann surface. When it will be automatically flat, though. Okay. And now, so recall that any ethyl trivial bundle has a tautological flat connection with finite monodromy. Therefore, we get a homomorphism. Ethyl fundamental group. So these correspond to ethyl fundamental groups correspond to flat connections with finite monodromy. Yeah, so ethyl trivial bundle with a connection, but the sorry, what I'm saying, it corresponds to ethyl trivial bundle, so it has a tautological connection, so I can any E. Sorry, I'm sending E to E, comma, D. I D the tautological connection. We saw that any ethyl trivial bundle has a tautological connection. So this is what is called faithfully flat, but better to use the word surjective. You can say it is surjective. Now, for example, it gives a map of characters of the group to characters, and this image is precisely the characters, homomorphism of characters. Consider the homomorphism of characters given by this map homomorphism, and then image is precisely the characters of finite order. Anyway. Okay, so now I recall theta, the pro-algebraic completion of the topological fundamental group. So representation of the fundamental group correspond to flat connections, So you take the category of category of flat connection. You see that this is a Tanakian category. So and so you take the corresponding algebraic group, which is this, which is also the just completion of them. So now we have a homomorphism, right? From, let me then recall the notation. 5. No. Let us go beta from EM not to theta. So is that any E comma B flat bundle. It is I've just now I said that it is a pro-algebraic completion. It corresponds to, but on the other hand, it corresponds to flat bundle. Sorry, that's what I have said. sorry. Sorry.
Flat bundle, right?
Sorry. Yeah, all flat bundle. All flat bundle, not necessarily ethyl trivial. These are. ED goes to E. Oh yeah, I should do that. I should have said. Oh, sorry, I messed it up again. I should. In this case, I should take integrable connection because it is not. Earlier I said just holomorphic connection. Actually, I had in mind X is now M is the Riemann surface. Compact Riemann surface. So any connection, holomorphic connection is automatically flat because there is no two form. Holomorphic two form. So now I'll state a theorem. So this is the any representation ED goes to the itself. ED is a flat. This here the representations are all flat bundles, and here it a representation of all flat bundles such that underlying bundle is ethyl trivial. So this is sub, and so the homomorphism is opposite direction.
Presentation. So taking representations of.
Sorry. Yeah. Sorry. It is not this map.
Then it goes the other
Yeah,
way.
it's a home. This given by map of functor of between the two categories given by the functor that sense. Sorry. Theorem with that is a Dumistrescu. Dos Santos, Heller, Lynn Heller, Sebastian Heller. Suppose phi is a Riemann surface homeomorphism. Orientation preserving. That's not needed actually. Orientation preserving homeomorphism such that what? It maps homeomorphism gives homomorphism of fundamental group, so it gives a map of the completion. Homeomorphism produces a map of pi 1, so it's a completion. It gives a map of theta of m x naught to theta of n phi x naught. Phi lost. Suppose it descends. I have a homomorphism from this. Suppose it descends. Then suppose such that it descends. This homomorphism produces homomorphism below. Then M is biholomorphic to N. Now I'll. How much time do I have?
20 minutes.
20 minutes. Okay.
You started at 15. You started at 15.
Okay, thank you. Now I'll recall some paper which is very influential for me. I mean, for us, Bart and Derwin. Victoria Hoy and Bangalore. So I'll recall their theorem result. So M is a bad notation. M is now kind of a modularized space, so not any. We are not MSL2. I take all pairs X, D. Where X is a element of the triangular space. That means you have a not only a complex structure, you have a fundamental group up to outer automorphism. Up to inner, and then D is a X is a Riemann surface element, and D is a holomorphic connection on the trivial holomorphic bundle X cross SL2C on the trivial bundle. Yeah, genus is fixed. Fixed. Sorry, yeah, fixed genus. Taken. Now you have the monodromy map, right? Given a, we saw that given a, I said holomorphic connection, but any holomorphic connection of Riemann surface is integrable. So we get a map from M SL2 to homomorphism. Sorry, I should have. It's better to put irreducible. irreducible holomorphic connection so that I can form irreducible homomorphism from pi1 of x to SL to C. Quotiented by SL to C. You have the monodromy. From the holomorphic connections on the trivial bundle and the Riemann surface is moving for all Riemann, and then from there the monodromy. Theorem of the C. Derwan, Hoy, and Frank-Lore. They prove the following. Take G is equal to 2. Then this map, let us give a name to this, call it gamma. Then gamma is a local biholomorphism. And then they showed that for constructed examples for higher genus, for some higher genus, G is 7 or something, G is equal to I think 7 or something. This is not an immersion, not local biholomorphism, not an immersion. No, I forgot to tell. This is holomorphic map. Monodromy is a holomorphic map. So sometimes it is not an immersion. So it is not higher genus. You cannot expect it to be local biholomorphism. But we prove the following thing with Sorin Dmitrescu. Take M. Instead of SL2, we'll take MG, G complex reactive. Now we can define the same thing, right? I can take X, comma D, where X is in TG, and D is a, just only thing I have to change is that trivial bundle on X cross G. So if I define the definition of MG is just change the SL2 by G, substitute, so this is MG. And I still continue with the irreducible, of course. So now in that case, we have the gamma from MG to home irreducible pi1 of X to G percented by G. G is reactive. Consider this. Gamma is generically immersion. If dimension of G is greater than or equal to 3. This condition, G greater than or equal to 3, of course, is necessary because, for example, if we take GM C star, so this becomes MG becomes, sorry, 3G minus 3 plus G, 4G minus 3, and this becomes 6G minus maybe 6G. No, sorry, what I'm saying, 2G. So it is 3G minus 3 plus one form, so 4G minus 3, and characters into this is 2G. So this cannot be a C star, it cannot be. And when it is C star plus C star, again you have 3G minus 3 plus 2 from that means 2G. And here you have 4G. So again, you cannot expect dimension 1, dimension 2 for G. You cannot expect to be local immersion. This cannot hold for dimension. But for as soon as you hit 3 or go beyond that, then this is a local immersion, generically an immersion. Well, there are now they asked 2 questions in the paper. Question one. Why? Is there ED in MSL2 says that whose monodromy lies in SL2R. And question two there. Can you have, is there same there? Is there ED in MSL2 says that whose monodromy, image of monodromy, whose image of monodromy has a discrete imaging, has a discrete image in SL2C. Why did they ask the question, or what is the reason for that to sorry? So I have to recall some result. Some result of Huckleberry. And Margulis. Take co-compact races. Gamma. Co-compact. So SL2C. What gamma is a compact manifold, compact threefold. Take. Then SL2C mod gamma does not contain any closed complex hypersurface. So this is Huckleberry Margulis. So they ask, and the question, the natural, does it contain? Can it contain closed Riemann surface? Of genus greater than or equal to 2. 2 is necessary because first of all, genus 0, of course, it cannot contain because of motoballistic property. It map from P1 to SL2C mod gamma will leave to SL2C and SL2C and affine variety. So there's no non-constant map. And there are genus 1, you can construct gamma such that SL2C mod gamma contains genus 1. So the question is for genus, because basically you take the diagonal matrices in SL2C, that is sister, and then lattice intersect co-compactly, so that diagonal modulo the gamma intersection is to diagonal modulo. The image of the diagonal modulo gamma is a genus 1. It can happen. You can produce a lattice such that. So now ATNG is at a he had a way to address this question. Suppose take SL2C mod gamma. This is a principal gamma bundle, right? Going to question. So gamma is sitting inside SL2C, so I can take the SL2C bundles. So that corresponds to this is SL2C quotiented by gamma. So associated bundle is this. This is when you have a subgroup G mod H, take any group, G mod H is a principal H bundle over G, and then you look at the inclusion of G to H and construct the G bundle, then it comes to the tautological trivialization. Basically, you take X comma Y goes to X comma XY. Using that, this is SL2C presented by gamma times the trivial SL2C. It becomes a trivial. So now suppose I have a map from Riemann surface to compact Riemann surface to this. So I can pull back this trivial bundle. This is a discrete structure group is discrete. So this has a tautological connection because there's no real algebra. So and this gives a connection on this non-trivial connection. So I pull back the SL2C bundle with the trivial SL2C bundle with the connection. So I get a trivial SL2C bundle and get a connection on this by pullback connection. And what is the connection as a property? Is monodromy lies in the lattice gamma, because this connection has monodromy gamma. So if monodromy lies inside gamma. And this connection, if you use a non-constant map, it has to be irreducible. You can easily see that the connection has to be irreducible. So now, giving a map is equivalent to produce a holomorphic connection on the trivial SL2C bundle, irreducible connection on the trivial bundle whose monodrome is contained in a co-compact lattice. Existence of F is equivalent to giving an irreducible connection on the irreducible holomorphic connection, sorry, on the trivial bundle whose monodromy has its image contained in gamma, whose monodromy homomorphism has its image contained in . So that was the motivation for them to study for them, sorry, for them. So now I just take two theorems with Dumitrescu, Heller, Lynn Heller, and Sebastian Heller. We construct D on construct X and D on X cross SL2C. With monodromy. Image of the monodromy is a Fuchsian group. Work same genus, namely monodromy coming from the uniformization of a Riemann surface, so it's contained in SL2R. In particular, it is a lattice. I mean, not lattice. I mean, discrete subgroup of SL2R, SL2C, which is contained also in the real part, SL2R. So then, finally, we have this. Second theorem. There exist X and D as before, such that whose monodromy irreducible is contained in a co-compact lattice in SL2 modcom. Co-compact lattice in SL2. So in particular, you can have by G's, you can have curve contained in Riemann surfaces of genus greater than or equal to 2. Genus greater than or equal to 2. So I'll stop here. Thank you for your attention.
Thank you. This result has a flavor of quasi-Fuchsian representations that somehow you are obtaining from this Fuchsian one and the element Heck-Muller, the not relation.
No. Cannot say that. It is co-compact. They are not co-compact. Is not quasi-Fuchsian. It is.
No, I'm not saying compact is quasi-Fuchsian.
No. I'm not. I understand. I
know.
know. Yeah, maybe often it's not. So I cannot say no. It is not quasi-Fuchsian. No, I don't think. I don't know. I don't know the answer to the question. I don't know the answer. It can be, and it may not be.
My question was right, imprecise. Is it a flavor of something? But
no.
yeah.
So no, I don't know the answer. No.
Yeah, and this MSL2, this map gamma that you have to the character variety for SL2C, irreducible representations in particular. But if we consider the non-abelian Hodge correspondence with Higgs bundles, can you find a path relating this MSL2 with Higgs bundles?
We could not get hold what Higgs bundle correspond to. What is the Higgs bundle as translation of the statement that the underlying holomorphic bundle is trivial for the representation. What it translates into with the non-abelian, we could not. We tried for some time, but we could not even get a candidate.
Thank you. So, this theorem here. So, you're saying that in some sense we have these two. I mean, we have a Lagrangian, a well-defined Lagrangian, which is the Fuchsian representations in the moduli space of character varieties, if you like, and then kind of fixing the trivial bundle is not very well defined, but it's a bit like having another Lagrangian inside that space. So you're showing somehow that these two Lagrangians intersect. Is that right?
Just a second. Let me get it.
I mean,
SL2 representation. Why do you say Lagrangian?
Well, so if you're looking at an intersect, you've got a Fuchsian representation. So we're looking at SL2R connections, right? So inside the moduli space of SL2C flat connections, we have this as a Lagrangian, but we also have
oh yeah, not character variety. You are looking at the sorry. So yeah, you're looking at the connections. That's why it's Lagrange. I got confused between characters. So okay.
Well,
yeah,
okay. So I mean,
yeah, Lagrange. Yeah.
So inside the SL2C picture, it depends which symplectic form you take. Right? Yeah. Okay, that's right. But you have these two mid-dimensional spaces. One is not very well defined, if you like. You're taking a trivial underlying bundle.
Yeah.
I mean,
yeah.
Morally speaking, you have some kind of foliation.
Yeah.
But you're saying that these two mid-dimensional objects have an intersection.
At an intersection, yeah. That's right. Yeah.
Yeah, the question. Okay.